Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you have chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome again to our third of the Distinguished Lecture Series. Today we have Professor John Hennessy from Stanford University. Another one of these great presentations which you don't even pay for directly. Only there. John is another brother of mine. He's from New York City. You can think of us as fellow gang members, but of rival gangs, because he was from Long Island and I was from Manhattan. Where he got interested in this entire field is his father is an electrical engineer who had been working in the defense industry. Returned to school to study electronics, which was an up-and-coming field in those days. At the same time, John got exposed to electronics, and he was intrigued by the fact that things were going from analog to digital. He also found it was possible to buy some logic circuits at a relatively inexpensive price. And so he began to tinker. One of the first things he did in high school with a buddy was to put together, out of surplus relay, a machine that could play tic-tac-toe. And then he also got together and basically built a small computer, which for him was a major project, out of some very high integration chips. In those days, you can get about 100 transistors and about 4 2-input gates on a chip, highly integrated. And he made a machine out of that. The fact that he was able to put that machine together turned him on to computers, and so launched him into this area. Went to Villanova for a bachelor's degree in electrical engineering, and there was an especially good situation. He found a graduate student who had come back from industry, from Burroughs, who was in fact building a machine to do some microprogramming which the user could get his hands on. John worked on that project, as well as for the computer center. Now, he worked on the computer center, but at night, when the light was low, he found he could borrow some time. And of course, he managed to borrow some time and worked through much of the night. He perfected the art of waking at 8 a.m., showering, eating breakfast, and to be in class by 8:30 a.m. He still does that today, he tells me. In addition, he had read the OS-360 literature and found that he could introduce some small little additions to his code. So when the operating system returned the program to the user, it returned it in supervisor mode. One of the early hackers we're going to hear from today. John met his wife-to-be when he was a senior in high school, and he and she arranged to go to undergraduate universities, which were within 400 miles of each other. Except she was up near the Canadian border, New York State, in one of the most depressed counties of New York State. And he managed to spend his weekends riding on a bus, 18 hours one way, to go and visit her. I made the calculation, John, that's 22 miles an hour. Good weather. He then went on to State University of New York at Stony Brook to do his graduate work in computer science. He chose Stony Brook for the simple reason that they were one of the few organizations accepting students mid-year. And since he graduated in 3.5 years, he was out of phase. He got back in phase by going to Cindy. Enrolled as a computer science PhD student, and once again he was lucky. He found there a gentleman who had come back from Brookhaven and was producing a project to build a microprocessor to do bone scanning. Joined the project and immediately got a dissertation topic, something the envy of everybody in this room, right? 2.5 years later, he completed his work on real-time microprogramming system for microprocessors. He then took a faculty position at Stanford, and the rest is history. Now, what turned him on to teaching? When he was an undergraduate, he he taught a first programming course when he was, in fact, a junior or senior, I forget which. And he found that the main attraction, that really turned him on, the main attraction was the ability to interact with undergraduate and graduate students, bright young students who continue to pass by us aging faculty members as we go along. Constant fountain of youth. John has been at Stanford for 15 years. He taught his first undergraduate course last year. And he found he liked it again. And he promises me he's going to continue to do it from here on out. He's a member of the National Academy of Engineering. He's one of the co-authors of this book, which is now in its second printing. It's only been out a few months, Computing the Future. There's a copy in the archives. There's going to be more than one copy. You ought to look at it. Some rather interesting concepts there. His message to you, take advantage of new opportunities. You can't predict where they will lead. Now, understand that part of John's career was heavily influenced by the fact, in two cases, an undergraduate and graduate, that people from industry returned to university, got involved with the project, and did some real-world things. That's a very important component. That, in fact, is one of the directions this book is promoting: interdisciplinary work, access and interaction with industry, and hands-on operation. His talk today is Scalable Shared Memory, Multiprocessors, and the Stanford Dash approach. John?
So I think everybody nowadays is interested in trying to think about how to build large-scale parallel machines. Seems to be the thing to do. If you think about this problem for very long, what you'll come to realize is that the challenge is, how do you build the memory systems that can scale? How do you build the interconnection mechanism and communication between processors that can scale? The problem is not so much one of building scalable arithmetic units or scaling up the functional capability of the machines, but in fact figuring out what to do about memory. There are sort of two approaches you can think about. One is the very popular distributed memory approach, where we have private memories in the machine. The processors communicate by message passing, reasonably well understood. The other approach is to try and implement a single address space. Notice that I say here a single address space implemented with physically distributed memories, and this is why perhaps the name shared memory is somewhat misleading in regard to this, in that in order to get scalable memory bandwidth, one has to physically distribute the memories. You can't build a machine very easily and very cost effectively that has a single shared memory. So we're going to have a single address space across the machine, but we're going to distribute the memory. Point out to you that both approaches require attention to two things in particular. One is locality of access. The locality of access problem becomes fundamental because if I distribute the memory around the machine, I have to worry about how long it takes to access those memories. So locality of access is a critical problem. There's also a question of getting a scalable base interconnection technology so that you can build bigger versions of this machine. I think actually one could argue that the scalability of the interconnection technology is an area that's been progressing quite nicely. There's been a lot of progress, and so I'm not going to focus a lot on this and just hope that people working on this are going to continue to do great work. Instead, I'm going to try and focus on the locality of access problem. So why did we decide to pursue the single address space model? Well, first of all, there are a number of functional advantages. Probably the most obvious is that it's a better understood programming model. It's something that we have a lot of experience with. We know how it works. We like it. Well, we like it reasonably well, but certainly we like it better than message passing. That's clearly an advantage. It's probably easier to program, but for our viewpoint, one of the things that was really important is it's easier to build a compiler for it. And the way I think about this is that address space provides a mechanism, a uniform mechanism for communication. Certainly the compiler will try to optimize the locality of communication, but the address space provides a uniform mechanism. So rather than having two separate mechanisms, one local and one remote, I have a single mechanism for communicating. With a little bit of hardware help, we can also efficiently simulate other models. So by just adding a small amount of hardware to the machine, I can simulate message passing, for example, quite effectively. There are also some performance advantages, and two that we're really going to focus on this afternoon. One is that the communication of small data items can be made very efficient. And the reason it's so efficient is that it's integrated into the memory model. You already have instructions which communicate data in processors. Loads and stores communicate data. By integrating the communication in with the loads and stores and our entire memory management mechanism, which recall provides several important things. It provides naming of objects, and it provides provides protection, so that those functions are provided in the hardware. That can make communication extremely efficient. And I want you to keep that in mind because you're going to see that as that develops, as I explain how the dash mechanism works. We can also exploit caching, which is sort of going to be an underlying theme here. Caching is just an extremely attractive way to try to improve and exploit locality. Because it works in so many cases just so well, and it's a fairly stable mechanism. So we can rely on caching here to try and help the situation. Now, of course, one can have caching in any machine under programmer control, and that can sit on top of a level of caching that the hardware can provide as an addition. We'll also see that caching can help us do load balancing as well. Now, the fundamental problem that one has to overcome is that as we make machines progressively larger, the time to access remote memories or communicate with remote processors is going to scale up. And this just gives you some typical numbers that you might think about, just to give you a framework in which to think. But today, a local cache access on a high-speed microprocessor might typically take one cycle. Local memory access anywhere from 10 to 20, and probably going up to 50 very rapidly in next-generation machines. Remote memory accesses might take anywhere in the region of 100 cycles. And if software has to get involved even in a fairly minor way, one might expect that if you have to communicate a message, for example, that might take anywhere from 500 to 1,000 cycles. The important thing, I think, to realize is while certain mechanisms can help reduce these times, the basic parameters of that equation, basic scaling up, is probably not going to be terribly effective, and you have to deal with the problem somehow and provide mechanisms to alleviate these long communication times. Keep in mind here that if even a relatively small fraction, say 10% of the accesses, end up taking 100 cycles, you've got a real problem to worry about, because that means that the average memory access time is increased by a substantial amount, roughly a factor of 10. So how can we deal with this latency, these long access times? Well, the first method is we can lower the frequency of long latency events. This is sort of the most obvious way. We can tell, this is in fact, you can think about doing this in a message passing machine, right, where you tell people, well, you have two ways to program. You can access local memory or you can send a message. Don't ever send messages because they cost an arm and a leg, right? And to first approximation, this enforces on the programmer's mind a programming model that says avoid doing these things that take a long time. So this is actually quite a reasonable way to think about things. You could also think about compilers dealing with this issue as well. You can reduce the latency, and again here, caching provides an attractive way to think about reduced latency because it makes local copies of objects which can be accessed with a lower delay. And one problem we have to overcome here, and what we're going to talk about, is what to do about cache coherency. And you can, of course, reduce the communication latency. There are lots of mechanisms for tolerating latency. I just put a couple here. When you overlap computation and communication in a message passing machine, you're tolerating latency by allowing that computation to hide the communication delay. You can also do this by prefetching, for example. I can prefetch an object, make a local copy of an object, and hide the latency. You can do it by multiple context, where you context switch between when a long latency event occurs and hide the computation time, hide the communication time behind it. Another computation, another thread. All different ways of hiding latency. Let's focus on the caching issue for a bit. Once you've decided that you want to try and use caching as a way to hide latency, you have to address the problem of what you're going to do about caching shared data. One alternative is to say, well, I'm not going to cache shared data. I'm only going to cache local data that's private to this particular process. And therefore, I don't have to deal with the coherency issue because it's only owned by one process. And some machines have tried to do this. The difficulty is that all the shared accesses are then quite costly. And you can have programs which instantly run, which have horrible performance because they have relatively high frequency of shared accesses. And that will limit the scalability of the machine. You can try and do the caching under software control. And in fact, when we started this project, that was our intention. Our intention was to try and pursue cache coherency under software control. The difficulty is that you've got to do this job exactly right. You can't afford to be wrong, or what you get is an algorithm or a program which runs and gets answers which are wrong, but you never know they're wrong. You'll just be the wrong value, you'll use the wrong data. We decided it was probably too hard to get this mechanism to work well enough. So we decided to try and exploit the direction of pursuing a cache coherency algorithm. Realizing that, of course, to the extent that you can use a software mechanism, the software mechanism can optimize the use of the hardware mechanism. Note there's a subtle difference here. The hardware mechanism, I like to think of it, in this case, as a safety net. So when you're up on the trapeze and you fall, because you can't optimize the coherency or eliminate the coherency, you don't fall all the way to the ground and hit it hard. You still get an answer, albeit the program may run somewhat slow. The challenge, of course, when you start talking about cache coherency in a large-scale machine is whether or not you can come up with an algorithm that can scale up to larger numbers of processors. Now, if you start from the viewpoint of a conventional cache coherency mechanism, then it's easy to understand what the limits of scalability in such mechanisms are. A conventional cache coherency mechanism, most of them just use a bus in the backplane here, and they use a snooping algorithm. So any miss through these caches is put on this bus, and every cache looks to see whether or not it has particular shared data on it, hence the name snooping. The important thing to observe about these protocols is that it's not the bus that's the limit. It's the fact that the protocol is inherently broadcast-based. The information about who owns shared copies of data is not in any one location. It's distributed around. This cache knows what it has, this cache knows what it has, et cetera, et cetera. So the only way to find out who has copies of objects is, in fact, to ask every cache. So you can make this bus as fast as you want. You can put down as many as you want. All you're going to do is you're going to end up saturating the caches rather than saturate the interconnection. So that becomes the key limitation. So what can we do about this? Well, the direction that we use and a number of other machines have recently tried to pursue is to go to what's called a directory scheme for doing coherence. And the basic concept, insight behind a directory scheme, is that what we're going to do is build a directory here, which is associated with the memory. So let's say each block or each line in memory has a directory entry associated with it. And the directory is going to keep track of, with a set of presence bits, who has copies of shared objects. So if this cache has a copy, there'll be an entry in the bit vector indicating that there's a copy of this particular block of memory in that cache. And then there's a dirty bit just to indicate the situation where we have a dirty copy of the cache line and we haven't written it back. And that just supports write-back caches. It's more or less a defect. The important thing to observe about a directory is that it eliminates the need for broadcast. The information is now contained in one location, namely this block in the directory, and that tells me everything I need to know about that memory location. The coherency algorithm, the easiest way to think about the coherency algorithm is that the hardware enforces a multiple reader, single writer discipline on a cache line or a cache block. And the way it does that is when we go to read a location, the directory can tell us who has copies. It's sort of a yellow pages, who has a copy of this particular cache line. And it keeps track of the fact that we've now read a copy of that cache line by making an entry in the directory. So we can have a whole bunch of readers, we'll get a whole bunch of bits turned on a bit thing. When somebody wants to write the location, the directory grants ownership to the writing node. This basically solves the write serialization problem. And then tells us who needs to be invalidated. Where are the other copies that we need to throw away? So we look in the directory, figure out who we need to throw away, and we send individual point-to-point messages to those other copies. No need to broadcast. Network topology can be anything you want, because we're going to send out the messages across whatever the interconnection network is. Now, the interesting thing, this is actually an observation that can be made about many topics in computer architecture, is that the directory scheme actually predates the Snoopy schemes. It's actually, there's an earlier publication describing directories for doing cache coherency that predates the development of the Snoopy schemes. So what happened? Well, Snoopy's work just fine. Snoopy-based schemes work just fine when you have a bus-based, small number of processors, you can afford to broadcast. So it's a very pleasant scheme in that. But it doesn't work if you want to scale the machine up and still maintain cache coherence. So we want to basically go to a directory scheme. Now it turns out that this directory scheme, as I've shown you here, has a major problem. It has a major bottleneck in it. Namely, the directory. All I've done is I've taken all this traffic that had to go on a bus and go to all the caches and now funneled it through that directory. So I haven't yet solved the scalability problem. So what needed to happen to directories was the observation that you're going to distribute the memory, just distribute the directory as the same time you distribute the memory. So when you have multiple physical memory modules, you can have multiple directories, each associated with that portion of the memory. And I'll show you some pictures of this, because this is exactly what Dash uses in a second. One of the interesting things is that these sort of distributed directory machines are sort of at the heart of a whole variety of machines. The Dash machine uses it, the Scalable coherent interface uses a version of directories, the MIT LY machine, and the KSR machine, which is kind of halfway between directories and snooping, but relies on some of the key directory concepts. And it's sort of the base mechanism that all these machines are using, with a lot of variations. But now, let me show you how this mechanism works in the context of the Dash machine. So in the Dash machine, the machine is built out of what we call clusters. Each cluster is basically a piece of a machine. It happens to be a shared memory multiprocessor, but don't worry about that for a second. That's purely an engineering trade-off. If you just thought about it as processor, cache, memory, and directory, that's a good way to think about it. So this directory structured memory is a portion of the machine, a single cluster, which is then replicated and connected with the interconnection network. This acts as the directory for this piece of the memory. The memory is just distributed around the machine by high-order interleaving of the address space. So you can just figure out by looking at the high-order bits which block of memory that address belongs to. And likewise, where the directory is for that piece of memory. The nodes are connected by a scalable network actually based on a Caltech mesh. So it looks very much like a message passing machine once you cut it here. These processors, this piece of it, including the memory actually, everything except for the directory block, actually is a Silicon Graphics 4D340, which is a bus-based multiprocessor that we've actually used as a building block. From an engineering perspective, the only really important advantage of putting these things in a cluster, there are a couple of advantages, but the two of them are that we get sharing within the cluster because we use an Illinois protocol that allows people to do cache-to-cache transfers. Probably more importantly is that you amortize the cost of the memory interface, the I/O, which happens to be in each cluster, the directory, the network interface, all that sort of thing, by putting 4 processors in a particular cluster. let me tell you what some of the other motivations behind this particular machine are. At the heart of what we try to do in building this machine is to try and understand what it takes to build an efficient implementation of a cache-coherent single address space that's scalable, and to understand what it takes to program that. How difficult is the programming problem? How much does the cache coherency help solve the programming problem? What's the interaction between the hardware and the software system? We've also tried to include some other latency tolerating mechanisms, which I'll tell you about briefly shortly. And the other key factor, which we'll see some data from, is you're going to build a machine in a university. You might as well throw some instrumentation hardware in. I don't have to sell it to anybody, so the fact that it costs you a few $100 extra a node doesn't matter. So Dash has a whole bunch of built-in instrumentation, which allows you to collect lots of data that you couldn't collect on any existing commercial machine. If we were to sort of go down one more step into the hardware, you'd see a picture that looks like this. Now I can show you how a coherency operation would occur in the machine. Within each node, the processors here, 4 processors, each processor happens to have a 2-level cache. The directory controller, which interfaces to the interconnection network. Main memory, there's actually distributed I/O around the machine as well. Now let's trace a miss that occurs in this processor, let's say to a memory location that's over here. And I'll show you what happens. So this processor does a memory access. It misses through these 2 levels of cache and appears out on this bus. This directory controller picks it up and says, aha, that belongs to a remote memory location. It creates now in hardware a message which is sent out over the request mesh for that particular location, putting the address in the message. Sent over the request mesh, comes over here, appears to this directory controller. This directory controller says, aha, this is a request for a part of my memory. So the directory controller will then create a memory access, acting kind of like a fake CPU sitting on that bus, and insert the memory access on the bus. The local memory will respond with the data. The directory controller will pick up the data, and after updating the state of the directory, will then package it back up in a message, send it back over the reply mesh. It'll get routed back to this cluster. This cluster will now get the message back and say, aha, here's the data I sent. It will dump it on the bus and release the processor, which has been sitting there twiddling its thumbs this whole time, completely unaware that anything's happened to it. And release the processor. The processor now gets the data back, and boom, the access is complete. You can almost think of this as a hardware implementation of message passing, where the messages are single accesses or single cache lines being passed around the machine.
John?
Yes?
If the data item were in the cache at the remote site, is there any advantage? And if it's not, is it placed in the cache at the remote site?
If it happens to be in the caches here, the caches will respond and override the memory. And that just uses the basic protocol that's in the machine. And the only really important reason to do that is that the data can be dirty in one of the caches here, in which case the memory copy will not be up to date. This has virtually no impact on the access time because, well, contrary to what you might believe, it's more expensive in most machines, or as expensive to get the data out of cache as it is to get it out of memory. And the reason for that is that when you go to get, although the cache access times are smaller than the main memory access times, when you go to get it out of somebody's cache, the first thing you have to do is tell the processor to back off, please. And the delay in doing that covers the advantage in access time. So you don't get much advantage out of doing that. But the coherency protocol will work correctly. As long as you've asked that question, now I can add the tricky case for you. So this will see. The following little nasty thing can happen. Because this is a machine with write-back caches, if I write a remote location, it can be the case that, let's suppose this guy writes a location, whose address is in this cluster, and this guy wants to read it. He comes to this directory. I have to read that copy, and because it's a write-back cache, it is the case that there can be a dirty copy somewhere in the machine other than in the what we call the home cluster of that memory location. Luckily, this directory controller tells me where it is. So we'll actually send a message now from this directory controller out to here directed at this cluster, which will fetch the data out and then reply directly to that cluster. So that's we'll see that kind of three-prong hop in a few minutes when I show you what the access times look like. Okay. Just to show you, this is real, honest-to-goodness hardware. This is one of the two boards that sit in the back plane. You'll notice it's lots of low-density Xilinx parts, and this is actually all the performance monitor here, and PALs. Here are the mesh routing chips, right, sitting right here. Here's the logo sitting under those parts there. Important things. This uses, one of the important things about this project is we've used state-of-the-art academic packaging technology. Ultra-high density here. Stuff. In fact, this is the cleaned-up picture I usually tell people. Normally, when we're running the boards out on the extenders, we have a set of old TTL magnets which hold this up and keep the pins from bending, and fans that go up here to keep it cool. But this gives you an idea what the machine looks like. This is actually a 4D340 here. Our boards are stuck in the back plane, and this is actually the mesh routing interconnect. Right? This is a 16 processor version of what we now have. We now have a 64 processor prototype of this machine.
Can you?
Go ahead.
It seems that for those of us that don't understand what's really involved in sending a message, that you are relying a lot on that your format of messages is a page and things like that. Why it's so easier than why don't you suffer the drawback of message passing system? Because eventually you are sending messages.
This is a very good question. First of all, if you look at what the difficulties in sending messages are, normally most message passing systems do a context switch to the operating system. And they do that both for addressing and protection issues as much as for anything else. Well, there is no addressing or protection issue here. The memory address gives you the location to send the message to. The protection mechanism is embedded in the fact that the memory translation hardware will not let you do a load or store to a memory address that you don't have correct access to. So that's a big part of it. The other part of it is, how does the message passing how do the messages really get handled in hardware? Well, there are a very small number of message formats, 8 or 10, basically. They're all of very short length. The longest message is a header and one cache line, which is 4 words long. So the messages are all short. They're a very small number of formats, and thus it's possible to build a mechanism in hardware that can correctly handle them. Now, despite all that, let me tell you that this protocol is on the edge of what one wants to contemplate building in hardware, mostly because it's much more difficult to debug it if you don't get the protocol right. Hopefully, we've actually done some work with David Dill and some of the other people at Stanford to try and focus on the issue of protocol validation, because it's becoming really critical for these kinds of machines.
John?
So, yes?
How does it get more complex with a read, modify, write instruction? Or do you?
We do support a read, modify, write. In fact, in synchronization, we support a number of synchronization primitives, fetch and add, for example. Fetch and increment actually is supported. Those are all supported by mapping the support into the directory mechanism. So they actually occur at the directory rather than at the memory. And you can think of the directory as a programmable state machine, more or less, that can be programmed to do a number of functions. It's got a bunch of memory there that it stores the bit vector pointers in, and you can program it to do the fetch and increment as well. It's just a question of how complicated that state machine gets before you have a hard time believing it's correct. So that's the major limitation, I'd say, there. Okay. Now, let me I want to tell you something about performance sorts of things. Before I do that, I sort of have to lay out the directory, the memory hierarchy, so I can give you some idea of how long, when I talk about remote access time, what we mean. When I go to do a memory access, one possibility is it hits in the processor cache, either the first level cache or the second level cache. Next possibility out, takes slightly longer, is that it hits in one of the caches of the processors in the same cluster. So that if it's any of those caches, those processors will respond with the data. Then we may go across an interconnection network to go to what we call the directory home level. The directory home level is simply the cluster that contains that particular memory address, where that memory address is mapped to, physically mapped to. This may be the same cluster. So for example, if I do an access to a memory location that misses, and that piece of that address is mapped to the local cluster, that's just fine. The only difference is that we won't see an intervening interconnection network access across here. But in the general case, we could suppose that that access is to a remote cluster. So I go to the directory. Normally, I'll get the data from there and then return. But remember this this three-hop situation where I have to go to yet another remote cluster to get the data. So each one of these creates a different level in the hierarchy with a different access time. This is definitely not a uniform memory access machine by any imagination. In fact, access times can run to do a local fill from the memory, so a miss in first cache, second level cache, and a fill from the memory takes 29 processor clocks. To do a 2-cluster fill takes 101 processor clocks. And to do a 3-cluster fill takes 132 processor clocks. Each of these bars, you can see the breakdown of where the time goes in a particular access. The important observation that I want you to see here is that a lot of the time is spent just going in and out of nodes. Not so much on the interconnection network. Right? That is a piece here. You can see the interconnection network of these light blue segments here. But a lot of it is just coming out of the node, into another node, access the directory, into yet a third node, and then back into the cluster. That's good because, well, it's bad that so much time is spent doing that, but the good news, if you're looking for good news and bad things, is that from the point of view of the machine scaling up, those times are fixed. Those are proportional to the base level hardware. While the interconnect times will scale up with a larger machine, they'll still scale slowly because it's a mesh. That will become less of a problem. So the longer access times will not be that much longer as you go to successively larger machines. It's still long enough to worry about. So one of the ways, in addition to combating this problem by allowing you to cache shared data, we also have a number of other mechanisms in the hardware that allow you to hide the latencies. The first is what we call relaxed memory consistency. And I'm going to give you a high-level picture of this. If you have questions, I have a lot of detail. We can talk about all the details. The basic observation you could make is that when I write a shared data item, if this program has been written by a good person who's been trained in computer science disciplines, you'll know that I have established some synchronization protection over that shared data item. So in particular, it's probably the case that if I go to write a shared data item, before you read it, we're going to somehow communicate by some synchronization. Now, if you make that observation, what you can do is, I can take my time doing that right, because you're not going to read the data. I can take my time subject to the fact that I have to have it done by the time I do any synchronization primitive which could allow you to go ahead. So what this allows you to do is it allows you to hide the latency of a write. Basically, writes can sort of pipeline out across the machine, take their time, they take 100 cycles, and nobody cares because the data is just filtering across the machine. So that's one of the ways in which we can hide latency in the machine. That works great for writes. Doesn't help you a whole lot on reads. The key mechanism we use for hiding latency on reads is a prefetching mechanism. A prefetching is like a prefetch is like a load instruction, except nothing happens. It has no semantics associated with it. It's sort of a hint to the outside world that it might be nice if you made a copy of the data item and brought it into my local cluster. So when you issue a prefetch on Dash, that's exactly what happens. It'll filter out through the cluster. The cluster will request the cache line remotely and bring a copy of the cache line into the cluster. Then if you subsequently access that cache line with an ordinary load or store, you get it in 20-odd cycles rather than 100-odd cycles. Now, one of the most important things in the Dash prefetch protocol, and one of the things that it's made its prefetch relatively useful compared to other prefetch schemes, is that the prefetch is maintained coherent. What that means is that if I prefetch a data item, and you subsequently write that data item, that's okay. You're going to generate, the directory will be marked, you'll generate an invalidation, and my prefetch will get blown away. This is what's called a non-binding prefetch. It has the advantage that I can sprinkle prefetches over my program without changing the semantics. So the program will continue to work correctly as if the prefetches were not there. Why is it so critical? Well, imagine a compiler trying to figure out where prefetches go. So it has a loop, and it's trying to hide 100 cycles of latency. So what it does is it picks up a load and moves it back 5, 6, 7, 8, 10 loop iterations, right? Which might well cause you to be concerned about whether or not the data could legally be read at that point. However, if the prefetch mechanism is non-binding, then I'm guaranteed that everything's okay. I can insert those prefetches. Again, it allows the compiler to be a little less precise. It guarantees that it's not going to change the semantics. There's also special support for sending data to a location. So for example, in Dash, you can actually ram a piece of data at somebody. So you can say, here it is, stick this in your cluster whether or not you want it. And that's useful for doing things like message passing. And in addition to fetch and increment, there's also support for queuing locks, which gives us a low overhead mechanism for doing synchronization. Now, let me show you some performance numbers. One of the things that we've been doing over the last few years is trying to build up a suite of applications that, shall we say, challenge parallel machines. And this has been a good exercise not only for trying to get some insight, but also for the graduate students. There's nothing like programming a parallel machine before you try and design one or build a software system for one. It brings a lot of realism and appreciation to the situation. So this shows you a bunch of applications that we brought up on Dash. Let me just tell you about a couple of these. We'll run through most of them quickly. Well, there's the mandatory blocked matrix multiply. This is required to show what you can do on a high-end machine. This is a volume rendering code, which actually this is the fastest anybody has managed to do the volume rendering. It runs faster right now in Dash than any other machine, despite the fact that they're clearly machines with more processors. Fast multipole method. We've done a lot of work on n-body codes, both for things like astrophysics as well as molecular dynamics. So fast multipole method. Barnes Hut, which is an n-log-n n-body code doing an astrophysics simulation. Water, which is molecular dynamics code. Radiosity, which is a fast n-body algorithm used for doing a radiosity calculation in graphics. And it's an interesting computation. Cholesky, sparse Cholesky factorization. Locus route, I'm going to come back to PSYNC4. Locus route, which is a simulated annealing placement and route application. Let me talk about these two here, MP3D and PSYNC4. These are two variations of the same application, which is actually a wind tunnel simulation designed for simulating flight of the shuttle in the upper atmosphere. So you're simulating things in high up in the atmosphere, small number of molecules, but things moving at very high speed. This is the initial version of the application, which was ported almost directly from a version that was designed to run on a Cray supercomputer. What this application does is it takes a big 3D space, puts an object in it, and then shoots a relatively small number of particles at this object, and computes the turbulence effects and various things of this form. Now, The way this is run on a Cray is that you pick up this 3D space and you ram this 3D space, which is quite large, say 1,000 by 1,000 by 1,000 maybe, through vector pipelines of the machine. Well, this is great because the Cray can grab all that data from memory, zip it through the vector pipelines, and put it out. But you move this to a parallel machine like this, and it's a disaster because it's got all this data, it's got no locality, it's horrible. So, we tried a bunch of things to reorganize this. One thing you might say is, well, why don't you pick up the particles and assign the particles to the processors, and then have each processor work on a queue of particles? Of course, what happens here is that the surface is sitting in there, and the particles, as they hit the surface, start moving all around, and start moving in different parts of the space, and hence have terrible locality. So you can say, oh, well, what you should do is block the space up into subblocks, and give each processor a hunk of this 3D space, which, of course, you try that, and then you realize that there are the little areas near where this object is sitting in the wind tunnel that have a lot of computation to do because there are a lot of collisions occurring. And there are the objects up near the top of the wind tunnel where there's a nice laminar flow and there's no work to do. Right? So finally, we ended up reorganizing the entire program into a hierarchical object structure that now has subcubes and uses the subcubes as a way to load balance the computation, but maintain locality. So if some subcube, some processor has a group of cubes that all of a sudden starts getting a lot of colliding particles in, it'll start having its subcube stolen away by other guys as it gets behind in the computation. And that improves the performance quite a bit. Now, let me show you some more ways to look at the performance of this. What I'm going to show you are some performance data that's been collected on water and on this MP3D problem. And then you'll see exactly why the machine performs poorly on MP3D. As I said, we have in the machine a bunch of built-in hardware instrumentation. That allows us to basically see every single thing that comes out on the bus of the machine. And this is a real-time performance monitor which can read that data and display on a screen what's happening in the machine in real time. This little quadrant over here shows you, see it's mostly green, that's good. It tells you most of the processors are active doing real work. This shows you what's happening in each cluster with the red and the yellow showing you how much of the time the machine is stalled. So you see that's pretty small. And then over on the left here is a distribution of the remote access times. How long is it taking to get remote data? So you see that these distributions are fairly heavily skewed right around 100 here, and then a small blip around 130 out here, which says that there's not a lot of contention in the machine. And as I said, the water application runs quite well. Here's MP3D. So you can see here, first processors are idle half the time waiting for remote memory locations. Lots of red, lots of yellow, bad. And here you see all this activity here. There's a lot of contention occurring in the machine. These access times are being skewed way out here. So you can immediately determine that this application isn't running so well. Now, question?
Yeah, what's the deal with cluster zero?
Cluster zero is different because the way this works is basically with a distributed loop mechanism. So there is a master process which runs along, does a bunch of sequential things, then comes back to the next iteration, fans everything out, then it does a little bit of sequential stuff, fans everything out again. So cluster zero is seeing some of that activity and hence also it sees better performance in that part, less stalls. There's also a load balancing issue here that part of what you're seeing as well is a load balancing issue. Cluster zero just gets ahead a lot, and hence these guys are behind from a memory distribution viewpoint. One of the interesting questions that a lot of people have asked us about this machine is, what is the programming paradigm? What is the programming strategy somebody should have in mind for this machine? In a message passing machine, there is some fairly clear programming strategy, right? Don't ever pass messages, do a lot of local computation. That's a reasonable, despite the fact it's somewhat crude, it's actually a reasonable programming strategy. So kind of asked this question as well. One observation we've made is that for most programs, paying attention to temporal data locality is sufficient. On these applications, the shared data is distributed round robin on a page basis. There is no attempt to allocate shared data to the cluster that's trying to access the shared data. All the reduction in access time is happening because the caches are making local copies of shared data. Right. Hence, what we can say is that if you can pay attention to temporal locality, that's probably good enough to make the program run well. You probably don't need to worry so much about data distribution if you have good temporal locality. It's not usually a factor. It is in some, but most applications it's not usually. I also want to point out that you have to have good temporal locality. It doesn't matter whether you have a mesh passing machine or a shared memory machine. If the caches on the processor that allow the processor to get to its own local memory don't work reasonably well, the application is going to run terrible. The sequential performance is going to be horrendous. So this is you're going to have to pay attention to this in the normal way of thinking about machine learning.
Excuse me.
Yes?
Isn't data distribution important for load balancing purposes at least, even though it may not be used for
Distributing the computation is important for load balancing purposes. I mean, it may not be that you need to distribute the data to create that load balancing. I mean, probably you can say that some data distribution is important for eliminating hotspots. If you put all the shared data in one place, I mean, then you're going to create a hotspot. If you view the distribution of data as also inferring the distribution of the computation, as it does, for example, in Fortran D kind of mechanism, then yes, it's important. But we don't attach those two together. We sort of break the link. So this leads us sort of to what we might imagine as being a tentative programming strategy. You take a parallel program, you port it to the machine, then you tune the program to improve the temporal locality. I put quotes around tune because sometimes tuning involves more than just improving the way a loop runs or something like that. It may actually involve replacing an algorithm or data structure the way we had to do with MP3D to get decent performance out of it. And then only if you need to pay, you can pay attention to memory distribution. You can use other latency tolerating mechanisms to put prefetching in, other things. But for a lot of applications, you may not ever need to do that. Now, one of the things that's pretty obvious is that the memory hierarchy and the behavior of the machine can be quite complicated. In particular, if you have to explain to somebody who doesn't want to learn a lot about caches and cache coherency and all kinds of stuff like that, how this machine works, you're going to have a very unhappy programmer. Well, maybe that keeps down the number of programmers. So,
Excuse me.
Yes.
Can you define exactly what you mean by temporal locality in this case?
sure, what I mean by temporal locality is that the object that there's high probability that you've already accessed the object you're going to access next.
Okay, but then two processors reading and writing away at a single location would constitute temporal locality.
No, within a process. I'm sorry, within a process.
I know, but two processors banging away at the same location would constitute two instances of temporal locality.
That's true, that there is a full sharing effect here that you may have to worry about.
So it's not, I guess, either...
If you choose a small enough line size, full sharing is not usually the problem. But as I said, this is usually enough. There is a spatial locality issue, which if you paid attention to spatial locality, you would capture that, you could attack that full sharing problem that way. Which, you're absolutely correct, this is sometimes a problem.
Or true sharing. I mean,
and true sharing. Well, if the true sharing has good temporal locality, yes, there is a problem you can get in trouble here with true sharing. See, no, if the line is bouncing back and forth, then you don't have good temporal locality of true sharing. You've actually got data bouncing back and forth.
But each processor separately, I don't mean to push too hard on this definitional issue, but temporal locality seems to me to be defined different ways by different authors, and I didn't know if you had a sharp definition in mind that was sufficient for what you were claiming here. That's all.
It doesn't eliminate the full sharing problem. It is true that there are potential full sharing problems where two people share a line and write it back and forth. Now, whether or not you would view a computation where you were writing a shared data item frequently and I was reading that shared data item frequently, whether or not you would view that computation as having high temporal locality is somewhat questionable because there's obviously communication going on back and forth. Okay. In any event, if you want to really push this kind of notion of put the application up and sort of incrementally develop it on the machine. Put it up, see how it runs, improve the parts that don't, ignore the parts that run well. You obviously need some tools to start attacking this. So we built some tools. This is actually a screen photograph of a tool called MTool that we built for this machine. And we use it on other machines as well, but it's particularly useful on a machine like Dash. And what MTool does is it instruments the program with software using being very careful about where it puts its instrumentation so as not to perturb the parallel behavior of the program. And then keeps track of the amount of memory overhead, synchronization overhead, load imbalance, parallel overhead, for example, if you're using a mechanism that has some additional overhead involved in parallelizing loops, for example, and can plot that information. So, for example, these are the procedures in the PSIM4 application. A procedure that moves a particle, a procedure that matches up other particles, a procedure that completes the loop and determines what the next step is. This black region here at the top says that's memory delay. That's a delay that's encountered because the system is waiting to do install, basically, that process install to do remote access. So MTool can plot this sort of thing up, give you information about how much time is spent doing real work, installed, and then can even take you down to the loop that's responsible for that delay time. So in the first step, it's still the programmer that has to get smart about rewriting that loop. But eventually you might think with this kind of instrumentation hardware that if you can find where the problem is, maybe a compiler can do it or the runtime system can somehow manipulate this loop so that it has better performance. So let me make a few concluding remarks, and then I can answer any other questions people have. You really look at what the key problems one has to attack in a large-scale multiprocessor. There's a problem of scalability, building a machine that's big enough. There's also the fact that if you don't have the word scalable in your proposal somewhere, you'll never get any research funding. Closely linked problem. And then there are problems, the data locality and distribution, how you distribute that, how you tolerate latency. Those kinds of problems are all bundled up together. Synchronization and load balancing problems, dealing with that. And of course, good old programming complexity. One would like it, the situation to be that it wasn't tremendously harder to program these machines than to program conventional machines. One would like that once you write a parallel program for a machine, it ports easily to another parallel machine. So we've tried to attack these problems using some combination of hardware features together with some software support. Hardware support for single address space and coherent caches to allow you to use caches to tolerate latency and to keep a single communication paradigm, a single programming paradigm. And then obtaining scalability by using a directory coherence protocol underlying that and a message network which allows the machine to scale up to larger size. And then software support to help make it easier to use all these things. Let me say that this is a humongous project, at least probably by academic standards, and certainly by ours. There are a whole bunch of faculty, myself, Anup Gupta, Monica Lamb, Mark Horowitz, a couple staff members, a bunch of graduate students who've slaved long and hard on making the machine. We were lucky enough to get 2 graduate students early on who had actually come from industry, which were really key to being able to build a machine that worked reasonably reliably in a small amount of time. And we got a lot of help from Silicon Graphics sort of as a partner in the whole project, both doing some fabrication as well as guiding us through the intricacies of their design so that we could go in and modify their hardware. And it's only when you bring all these people together and get them working on a common focus that you get something like this done. So that's sort of a short, actually relatively high-level picture. I'll be happy to answer any questions anybody has at any level of detail that you care to ask about. I can't see people in the back so well, so jump around or something, or just shout out.
Did you have any operating system structures in mind that you were designing toward?
We didn't. So one of the things that I sort of did mention is, well, what happens with an operating system on this machine? So the good news is that it's a cache coherent single address space. So one graduate student ported the SGI 4 processor operating system in about 3 months to run on the machine. The most difficult problem you have to deal with is you have to boot up now all these clusters, which before was a relatively small problem, becomes a little more difficult. So that's sort of our top level operating system thing. And most of our focus since then has been on hooks, so that user processes can explicitly allocate data within a particular cluster if they want, support for interrupts across the machine, support for bringing the machine up, subdividing it. Of course, this works fine as a multi-programming machine because it is a single protected address space. The direction we're kind of moving now in the operating system region is to try and ask interesting questions about I/O. You'll notice that I/O is distributed around the machine, which I'd argue is exactly the right way to scale your I/O system. But it presents some very nasty programming challenges, especially if you think of I/O as coming from a single source and going to a single destination. So that's the direction we're moving now, but we've just started doing that.
What factors affected your decision concerning the line size?
The fact that the line size is 4 words is actually dictated by the underlying SGI hardware. So we couldn't have changed it if we wanted to. This is it's kind of a stroke of luck, because at a line size of 4 words, false sharing problems, which can arise with longer lines, basically don't occur. They're in the noise. They're not a big issue.
Is it possible to get better performance with larger lines?
Yes, if we increase the line size, we would see performance improve, certainly for 8 words and probably for 16 words. And then we would see false sharing effects probably dominated out. That's what we've seen with our simulations. So it would be beneficial to increase the line size somewhat.
What about scalability in physical dimension? How far apart can you put these clusters and still expect it to perform?
That's dictated to a large extent by the quality of the interconnection network and how fast you want to run it. We use a version of Chuck Seitz mesh routing chip, and so in a room you certainly don't want to be further away than in a room with those chips as it is. But one could imagine an interconnection technology that would allow you to separate them further apart. There are some issues to be dealt with in the machine as you separate things further apart. For example, we have various things like timeout and things like that. And if you change the interconnection technology, you would have to adapt those. But otherwise, I think it's not dependent on how that interconnection technology performs.
How many CPUs do you scale?
This prototype can scale to precisely 64. And the reason for that is that we run out of address space. We believe that it's possible to build machines of this sort that scale to thousands of processors. The problems to be overcome in doing that, first is to get more address space. So the way you do that is you go to a processor with 64 bits of memory addressability rather than 32. See, I thought about this ahead of time when I was... Then the next thing you have to do is you have to come up with a mechanism to scale the directory. In the current machine, the directory occupies about 10% of the gates/memory count. However, the current directory scheme doesn't have good scalability properties. It basically, in one dimension, it scales as the number of processors, and the other it scales as the amount of main memory. So if you were to scale a machine up by adding more processors and more memory, the directory size would scale up as n squared, while the machine scaled as n. That's a bad thing. So one of the things we're doing is for the next machine, we're designing a scalable directory structure that squeezes both of those dimensions. And we expect to be able to design a machine with 256 to 1,000 processors that maintains about the same level of directory overhead, under 10% overhead in machine for directory stuff. So that's our goal.
Yeah, showing us the software tools that determine the source of latency problems. But you pointed out that currently programmers have put their own modifications and there's support that's available. Have you noticed improvements?
Well, we're pursuing a number of things to try and attack this problem. The two focus of two directions we're trying to attack. One is sort of more of a compiler-directed strategy based around both Jade, which is an extension of Fortran, or C, and you could imagine doing it for Fortran D or Cyberpoint's Fortran as well. That focuses around trying to decompose loop-oriented structures. So you take a loop-oriented structure and you decompose it. There's been a number of people who work on, for example, blocking algorithms, which do this kind of thing. You divide locality in loop-oriented computations. The other direction we've been focusing is on a parallel version of C++ that tries to encourage programmers to use the object structure to reflect the locality of their algorithm. So you can imagine talking about objects and keeping an object local on something and making most of the tasks that access that object run on the same location that the object is allocated. So those are the kind of two directions we're pursuing to try and push locality. Right now, programmers deal with it primarily by thinking about their algorithm structure rather than by, because we don't, in most of these applications, worry about memory distribution, initial allocation.
John?
Yep.
I sort of see an interesting trend here in research that I'd like you to comment on. If you look at your work, or you look at, say, the CM5 or other people's parallel processors, you can almost view them as kind of OEM or value-added research, where you're taking somebody else's processor, somebody else's interconnection network, somebody else's something or other, and throwing them all together and then adding some smarts and getting a processor. Do you see that? And Danny Hillis, at least, I guess, claims that they don't want to spend the money in their company to design a new processor because everybody else, Intel's got all the smart people and all the money to do it, and so why not just use their ideas or Sun's ideas or something?
Yeah, I think that certainly goes on in industry. I mean, and I think the people who've made the mistake of building their own processor are learning their lesson, right? The amount of dollars you have to build a state-of-the-art microprocessor, you don't want to think about building your own processor. And I think in a university research environment, there are even additional motivations you have to deal with, right? I don't want to build memory boards. I don't want to build I/O interfaces. I don't want to build a lot of that stuff. I didn't want to build an interconnection network. So what we try to do is exactly what you said. What can we steal? What do we have to modify? Can we get the modifications down to as small as possible with the experiment? And the big advantage from our viewpoint, it's kind of the same advantage that Danny Hillis would be looking for. Probably the overwhelming one is the time to market or time to complete the project, which I think that's the critical one. It's not just the money, but it's how long does it take to get the machine up and running and getting answers out of it and getting experiments done. And I think, and validating whether this is a good idea or a bad idea. I think this is really a direction that things are going to move as we try and do experiments on bigger systems, whether they be hardware systems or software systems. You have to try and figure out what's your value add, what's the part of the project you're going to attack. The other thing people will observe about hardware projects is that if you put too many variables in, the answer you get out is gobbledygook. Right? You can't tell what you really learned because all the things interfere with one another and you can't tell what were the good ideas and what were the bad ideas. So by trying to focus on a smaller number of things, we'll hopefully understand what the strengths and weaknesses of those ideas are.
So do you really see a sort of a balkanization of research in the sense that everybody's using Chuck Site's router and everybody's going to use a MIPS RISC chip or some such thing? And is that a good thing? It's great to get your system out, but is it a bad thing in the sense that that nobody's going to do interconnection technology research anymore, and so we all believe Sites has the best answer.
Well, I think he'll continue to do it. There's
Right.
some other guys around. He's got this student at MIT that thinks he knows better than his advisor, that'll continue that. So I think there are people around who will continue to do that. And the question is, what's the payoff in one of these areas? So, for example, now, what's the payoff in trying to do a uniprocessor design in a university? I mean, you'd have to have a unique twist on that to figure out what your value add is. So even if you take Anand Agrawal's Alewife project, I mean, his twist on it is to try and take this existing Spark and add multiple context to it. So even there, he's trying to build on top of some existing platform. There's right now, if you, for example, tried to do processor, just the thought of trying to do processor research on a uniprocessor when everybody's next generation processor is 3 to 5 million transistors, and the thought of it is just overwhelming. And so I think things have to move in that direction. I guess the question you always have to ask in this, and I think we've asked it, if you want to hear it, I can certainly tell you about it. What are the drawbacks of doing things that way? Well, I can tell you there are some real drawbacks of this, of building this hardware this way. We know how to localize them. One is that it takes us too long to get on and off of this stupid bus that's in the backplane of this machine. It was designed to be a non-split transaction bus. We had to hit it with a hammer. There's actually a signal that comes off that says whack. And every time a transaction goes out of the processor, we yank the whack signal, which backs the processor off. We had to make some very nasty, small but nasty modifications to each one of the processor boards in this design. On the other hand, compared to designing a processor board from scratch, it's small potatoes, right? I think we also see a lot more cooperation going on here. I mean, despite the fact that we're doing most of the work and adding the value, Silicon Graphics help here and there. Make sure we've made the processor mods correctly. Make sure they really work. Tell us more about the protocol. Give us documentation that's not otherwise available. That kind of cooperation, I think, is going to be key to trying to do larger projects in the future. Question?
Along the lines of the standardization, we all know that programming is the biggest bottleneck of using parallel architecture. So if the goal is to make them more widely applicable, do you have any views on where we are converging in terms of programming paradigm, or should we be designing architectures to fit a specific paradigm rather than designing an architecture and coming up with new
well, I think five years ago, or even 3 years ago, you would have said shared memory's dead for large-scale machines. Message passing will take over. So now I think there's been a change in that viewpoint. I think now most people believe that all machines will have some hardware support for shared memory. The issue of caches and cache coherency remains an open one. So we're still, there are still people who are dubious that we can build a large-scale version of this machine. So our job's not done yet. And we can build a large-scale version, let's say, that doesn't cost a whole lot more per node. So that's still a challenge. But I think there is some convergence between the shared memory and the message passing machine. Certainly if you look at the kinds of things that are being thought about in high-performance Fortran and Fortran-D, they very much put a shared memory paradigm down on top of the message passing machine. And from the point of view of the programmer, he thinks about it as shared memory, and there's at least hope that a compiler will make that all work out well. So I think there's some convergence there. I think there's also an understanding that there are times when explicit communication is really better. The classical example I would give is if you're trying to do something in linear algebra, like an LU decomposition, if you thought about the problem carefully and you really care about performance, you know exactly where every block of data needs to go at every point in time. And you can do better, if only because you break the hotspotting problem, than doing it by demand, essentially. So I think there's that kind of thought. People understand there's some important ideas there that need to be exploited. The other thing I'd point out is that the number of small-scale shared memory machines will probably get to be very large. both, say, desktop workstations, as well as the machine down the hall, the machine in the building, will probably all be small to moderate scale shared memory machines. They're going to have a big impact in driving what the programming paradigm is, because there'll be a lot more of those machines than there will be of the very large machines. So I think a natural, if you look at the whole rest of the computer industry, the software gets driven from the bottom up. It gets driven by the mass markets. So I think that has to factor into our situation. I want the guy who writes his small program and runs it on his workstation with 4 processors, takes the same program and runs it with 16 or 64 or eventually with 1,000, possibly having to tune it as he goes along to improve locality, reduce hotspots, improve the synchronization, whatever. But I think some continuum of programming paradigm is going to be quite important if we're going to accomplish the same sort of uniformity that we have on uniprocessors. So that's a remaining target. I think there's some convergence, but there's still a ways to go.
Well, John, we're hitting the 6 o'clock barrier.
Okay.
And take another question. Thank you very much.
Okay.